Well, percent by mass data is really mass data, and it's very easy when we have a percent composition to get an empirical formula. You just make the assumption that you have 100 grams of the compound. And if that's the case, then, like in this example, 60.002% carbon, that's like saying 60.002 grams of carbon. Percents can become grams if you just assume that you have 100 grams of the compound. So let's do this problem. Figure out the empirical formula for this compound. Okay, it's 60.002% carbon. So here's what that means. In a 100-gram sample, you'd have 60.002 grams of carbon. Hydrogen, 4.476% means 4.476 grams in a 100-gram sample. Same thing for oxygen. 35.522% means 35.522 grams would be in a 100-gram sample. Now that we have grams, we just change them to moles using molar mass. So for carbon, molar mass is 12.011 grams per mole. This gives us 4.9956 moles of carbon. For hydrogen, the molar mass is 1.008 grams per mole. This leaves us with 4.440 moles of hydrogen. And for oxygen, the molar mass is 15.999 grams per mole. This calculates to 2.2203 moles. Now our next objective is to find mole ratios based on the smallest number of moles. Well, oxygen gives us the smallest number of moles. It's 2.203. So we want a H to O ratio and a C to O ratio. The H to O ratio is 4.440 moles divided by 2.2203 moles. And this comes out to really, really close to 2. My carbon to oxygen ratio is 4.9956 moles to 2.2203 moles. This doesn't come out to a whole number, but it comes out really close to 2 1/4. So our formula, if we were allowed to have quarters, would be C 2 1/4 H 2 O 1. But we can't have quarters. So we're going to multiply everything, all the subscripts, by 4 to get a formula that's in whole numbers. 2 1/4 multiplied by 4 would be 9. 2 multiplied by 4 would be 8, and 1 multiplied by 4 would be 4. So there's our empirical formula. Try this one. Here's our starting point. Sodium's 32.37%. So in a 100-gram sample, that'd mean 32.37 grams. We could find its mole quantity by dividing by its molar mass, which is 22.99 grams per mole. This gives us 1.408 moles of sodium. For sulfur, 22.57% means 22.57 grams if you assume 100 grams of the compound. Well, the molar mass of sulfur is 32.066 grams per mole, and so this leaves us with 0.7039 moles. And oxygen, well, 45.05% means 45.05 grams in 100 grams of the compound. The molar mass is 15.999 grams per mole. So with grams canceling out, we now have moles for oxygen. And that number is 2.816. The smallest number of moles here is sulfur at 0.7039. So we want a sodium-sulfur ratio, and we want an oxygen-sulfur ratio. Sodium-sulfur ratio is 1.408 moles divided by 0.7039 moles. This number comes out really, really close to 2. The oxygen-sulfur ratio is 2.816 moles divided by 0.7039 moles. This number comes out really, really close to 4, within a few hundredths of 4. So that means it's sodium 2, sulfur 1, oxygen 4. There's the empirical formula. Well, this is an ionic compound, and we recognize this as sodium sulfate. Now, the molecular formula we discussed earlier isn't necessarily the same as the empirical formula, but its subscripts will always be whole number multiples of those of the empirical formula. So here's how we can find a molecular formula if we know the empirical formula and somehow we have the molar mass. The first thing you want to do is find the molar mass of the empirical formula. Calculate it out as if it's a real compound. Second, take the actual molar mass that we're given and divide that by the molar mass of the empirical formula. You should come out with a number that's really close to a whole number. Then multiply all the subscripts in the empirical formula by the whole number that's closest to the quotient you got in the last step, and you'll have your molecular formula. Here's an example. The substance has the empirical formula CH2O. Well, let's figure out what the molar mass of CH2O is. It's going to be carbon, 12.011 grams, plus 2 hydrogens, so that'd be 2 times 1.008 grams, plus an oxygen, which is 15.999 grams. All told, that comes out to 30.026 grams for every mole. Now it says here that the molar mass of this compound actually is 180.15 grams per mole. So the next step is we want to find out what's the ratio of the actual molar mass, 180.15 grams per mole, to the empirical formula molar mass, which here is 30.026 grams per mole. When we do the division here, this comes out to a number that's really close to 6. So instead of CH2O, we're going to multiply these subscripts all by 6 and get our actual molecular formula of C6H12O6. Try this one. Okay, here's our starting point. 24.8% carbon, again, means 24.8 grams if you just assume a 100 gram sample. So to change this into moles, we divide by 12.011 grams per mole, which is carbon's molar mass. This gives us 2.06 moles. For hydrogen, 2.08% means 2.08 grams. Hydrogen's molar mass is 1.008 grams per mole, and so we end up with 2.06 moles again. For chlorine, 73.1 grams is what 73.1% means if you have a 100 gram sample. For chlorine, 35.453 grams per mole is the molar mass, so we divide by that, and again we come up with 2.06 moles. Well, here's what this means. All the numbers are the same, so the ratios are all 1 to 1. So our empirical formula is CHCl, C1H1Cl1. What's the molar mass of that? Well, the molar mass of CHCl is going to be the molar mass of carbon, 12.011, plus that of hydrogen, 1.008, plus that of chlorine, which is 35.453. When we sum this all up, we come up with 48.472 grams per mole. That's the molar mass of our empirical formula. But the problem told us that the actual molar mass is 290 grams per mole. So we'll divide that by 48.472 grams per mole, and we'll find the ratio. Well, again, we have a number that's really, really close to 6, within a few hundredths of 6, so we can round to that. Well, that means we just multiply all the subscripts by 6. They're all 1s to start with, so we end up with C6H6Cl6.